Okay, so let me first introduce, it's my great pleasure to introduce Professor Dmitri Uzdensky. To give a brief introduction, he received his undergraduate degree in the Moscow Institute of Physics and Technology, and he received his PhD at Princeton University in 1998 under Professor Kolsrud. And then he has been in various places, including University of Chicago, KITP at Santa Barbara, and also Princeton University. And from 2009 onwards, he served as professor at the University of Colorado Boulder. And then recently, this year actually, he moved to University of Oxford as a professor of theoretical physics. And today he's going to give a talk on extreme plasma astrophysics, a shining new frontier. Take it away, Dmitri.
Great. Well, thank you very much. It's a great pleasure and honor to be here to give you this colloquium. I really would like to thank the organizers of this colloquium series for inviting me. And I understand it will be a kind of a broad audience, so I try to pitch my talk to general theoretical physics audience, but it will be mostly revolving two subfields of physics, which are plasma physics and astrophysics together. So plasma astrophysics is the area of this talk. And as you can see, I titled my talk Extreme Plasma Astrophysics, a Shining New Frontier, and I highlighted this word shining because, as you will see, it will be shining in the most literal sense, not in some, figure of speech, but in the literal sense. And I would like to thank also my collaborators. So thank you for the nice introduction. Indeed, I was at the University of Colorado Boulder on the physics faculty there for 15 years. And over these 15 years, I've had the pleasure and honor to have very fruitful collaborations with other scientists across the career spectrum. So including undergraduates, well, mostly graduate students, postdocs, researchers, and faculty members, and I would like to thank some of them here. By the way, can you see my cursor?
Yes, we can. Yeah, we can see.
Okay, great. Thank you. Yes, so I'd like to thank the members of my group. All right, so let's begin. Let's see. Okay, here we go. This is just an outline of my talk. First, I'll go through a few introductory slides, reminding you about the role of plasma physics in the universe, and then presenting my view of what do we mean by plasma astrophysics as a field of study. And from there, I'll go on to talk about extreme plasma astrophysics as a special term. And then I will focus just a little bit more narrowly on a subset of extreme plasma astrophysics, which is radiative and kinetic plasma astrophysics. I'll talk about what this is for, what the goals are, and the tools of this field of study. And then I'll focus on a specific example of a very important plasma physical process in space and astrophysical plasmas, that is magnetic reconnection, but specifically focusing on magnetic reconnection under the extreme conditions found in magnetospheres of neutron stars and in principal black holes, where radiative effects come into play. And then, if time permits, I'll talk a little bit about the future outlook of this area of research and summarize. Okay. All right. So first, just to remind everybody that even though the universe at large mostly consists of dark energy and dark matter, while ordinary matter take up only like 5%, it is this ordinary matter that produces all the light that we can see from the universe. And so we care about this ordinary or baryonic matter very much. And I would like to remind everybody that almost all of it is in the form of a plasma, right? Then, and we observe this plasma from astrophysical sources across a whole range of electromagnetic spectrum, from radio waves like this, for example, here, the huge jet in Cygnus A, very powerful active galactic nucleus with a powerful jet, through infrared, visible, X-rays, gamma rays, and so forth. So the entire spectrum of electromagnetic radiation. But even beyond that, we also now have the subfield of multi-messenger astrophysics, which utilizes not only electromagnetic light, but other so-called messengers, of which there are three non-electromagnetic messengers, gravitational waves, such as, we now have a fully fledged field of gravitational wave astronomy, studying processes like mergers of neutron stars and black holes through detection of gravitational waves. Neutrino astronomy, detecting very energetic neutrinos in up to peta-electron volt range at the Ice Cube Observatory in the Antarctic. And then finally, cosmic rays, which are extremely energetic, the most energetic particles in the universe, spanning 10 orders of magnitude in energy. And these are mostly protons, so charged particles. And they, of course, this is the oldest branch of multi-messenger astrophysics, spanning more than 100 years. However, we have a wealth of observations across electromagnetic spectrum and from all of these messengers. And we would like to understand what they tell us, but our physical understanding of these sources, I would say, lags behind the observations. And the reason, perhaps one of the reasons for this, is that understanding these electromagnetic and non-electromagnetic signals, how they are produced at the source, requires understanding of plasma physics, because it is due to plasma processes that particles that the cosmic rays themselves, or the particles that the cosmic rays that then produce very high energy neutrinos, these are plasma physical processes, except, of course, gravitational waves. So gravitational waves don't have any plasma physics nature to them. But everything else is the realm of plasma physics. So what is plasma? Well, as you, of course, all know, plasma is often called the fourth state of matter and is described as a just ionized gas of electrons and ions that flying around freely and carry electric charges and currents. They therefore generate self-consistent electromagnetic fields, and then these electromagnetic fields act with forces on the charged particles. So there is this coupled system between particles and large-scale electromagnetic fields. However, that is not all, right? The reason for this is that if you look at real astrophysical and space physics environments in nature, and by space physics here I mean environments within the solar system, maybe solar corona, solar wind, and Earth magnetosphere. So in all of these systems, and of course in the astrophysics sources outside of the solar system, the plasma environments are not simple. They're actually quite complex, multi-component systems. They have several constituents or components that coexist in the same place. And these include, well, the plasma itself, this thermal gas. And as I said, it's almost always coupled with some large-scale magnetic field here. However, in real systems, one quite often finds that in addition to sort of the thermal plasma, which may be still hot, but there are also non-thermal even much higher energy particles that we call cosmic rays. So there is a non-thermal, usually power law spectrum of particles at extremely high energies. And then finally, this plasma, at least in the most interesting cases that we care about, but I would say ubiquitously, never stays still. It always in motion. And one of the reasons for this is that plasma physics, of course, is rich with all kinds of waves and instabilities that cause the plasma move around. So there are all kinds of motions, including just large scale bulk motions. For example, the most common type of motion is rotation. Everything rotates in the universe. And then there are jets, like relativistic jets from active galactic nuclei produced by supermassive black holes. So these are large-scale motions. There are also small-scale turbulence waves that are ubiquitous and occur at all scales over orders of magnitude and wavelength and frequency. And then finally, and this is not quite universal, but will apply to the most extreme environments that are the subject of this talk, these plasmas are often bathed in a field of radiation. So they're permeated by photons across the electromagnetic spectrum. And interestingly, all these components, they are not always ordered with big separation in terms of the energy density and pressure that they carry. Quite often one finds that several or maybe even all of these components have comparable energy density and therefore cannot be neglected in this in the large scheme of things. A great example of this is our own interstellar medium, or ISM, in our own galaxy, where it turns out that the thermal energy density of the plasma is comparable to the magnetic energy density and is also comparable to the kinetic energy of turbulent motions. And it's also comparable to the energy density in cosmic rays. And finally, all of this is also comparable to the radiation energy density. So you can see it's quite a complex system. And importantly, all these components that have some energy density are interacting with each other. They're not just staying still, but they exchange energy with each other. And the way they exchange energy with each other is through what we call plasma processes or collective plasma processes. So that's represented on this diagram here. I hope you can see and appreciate the complexity of this field, right? So you have all these components, you have all these arrows going in all directions, connecting them to each other. So just to give you an example, for example, if you have a large-scale bulk motion, it can produce a shock. And the shock then takes the energy from the kinetic energy of the flow to plasma heat. It also accelerates particles, producing cosmic rays, also can produce small-scale magnetic fields, and so forth. And there is an opposite process of magnetic reconnection where magnetic energy density gets released and gets converted to plasma heat, accelerates non-thermal particles, including relativistic particles, and drives large-scale bulk flows. So all kinds of processes are involved here. There is a whole wealth of them. And basically, I would say that it is studying these energy exchange processes, collective plasma processes, that forms the realm of the field of plasma astrophysics. So that's what plasma astrophysics is about. Okay. Now, plasma physics and plasma astrophysics is sort of a mature field. There have been, thousands of people working on it, probably in the course of many decades. So by now we have accumulated a lot of knowledge of how these plasma processes, linear, nonlinear, under various conditions, how they operate under different conditions. And this knowledge base was produced due to a lot of efforts by many people, including theoretical research, analytical theory, a lot of numerical simulations, so computational branch, and even experimental plasma physics. So so we understand many of these plasma processes pretty well, and so it's natural to assume, or at least to hope, that we can apply this knowledge base derived from traditional plasma physics and apply it directly to high energy astrophysical plasmas, such as those around neutron stars and black holes, so the most extreme objects. And that would be the hope, but can we really do it? I would say that we should be careful, because such a direct translation would be justifiable or warranted if indeed these plasmas around the extreme astrophysical objects were really obeying the same physics, governed by the same equations. But I would contend that this is not always the case in very important ways that I'm going to describe now. Indeed. So traditional plasma physics, the entire plasma physics that has been developed both in the laboratory, including most importantly, the efforts to achieve thermonuclear fusion. So in tokamaks, in magnetic confinement nuclear fusion, and also to some degree in inertial confinement fusion, and in many other experiments, and also developed in space physics and solar physics in studies of, let's say, solar flares and geomagnetic storms and space weather in the Earth magnetosphere and its interaction with the solar wind. All of this is the playground for traditional plasma physics. And in traditional plasma physics, we deal with just electrons and ions as charged particles. These particles are non-relativistic and they're non-radiating. They're just flying freely. They do, of course, interact with electromagnetic fields at some large scale. But in contrast to this, in this new subfield of, let's say, plasma physics, that I will call extreme plasma physics, or extreme plasma astrophysics, as you will see later why, the underlying physics is much richer. In addition to everything that we had here in traditional plasmas, we also have more non-trivial composition of the plasma. So we will have electrons and positrons, for example, and sometimes they could be with ions, sometimes without ions. And then photons ought to be included alongside the charged particles on an equal footing, essentially. So photons, there is strong interaction between these charged particles, especially electrons and positrons, and radiation. And that manifests itself in terms of radiative cooling, radiative pressure, and so forth. Next, these particles and the bulk motions in these plasmas are often relativistic. That includes both special relativity and general relativity, certainly around black holes. And then finally, and I would say at the most extreme end of this extreme plasma physics, we are dealing with not just classical description, but also have to include some quantum effects, in particular quantum electrodynamics effects, such as pair creation and pair annihilation. In other words, in these plasmas, even the number of particles is not conserved, which is, of course, in traditional plasmas is the #1 conservation law. So all of these physical effects could be called exotic. You can see I wrote the word exotic here, but there is an asterisk. And this is because they are indeed exotic from the point of view of a plasma physicist who is not accustomed to dealing with them. However, they are not at all exotic to high-energy astrophysicists who have to deal with them, on a daily basis, essentially. And indeed, the main application of this extreme plasma physics are to objects like astrophysical objects like neutron stars and black holes. And in a surround of neutron stars and black holes, there is a plethora of phenomena in all kinds of systems where these exotic plasma effects come into play. And this includes magnetospheres of pulsars, magnetars, which are the most magnetized objects in the universe, accretion disks in the case of accreting black holes, accreting neutron stars and jets that emanate from these systems, and then powerful cosmic explosions such as supernova explosions, gamma ray bursts. More recently, of course, neutron star mergers have achieved a lot of exposure even for general audience due to the connection to gravitational waves. But what happens during and after this merger involves a lot of sophisticated plasma physics, including these effects. And finally, such conditions have existed in the early universe in sort of a small fraction of a second after Big Bang. And finally, I would like to say that even though we are motivated to study the behavior of these extreme plasmas by high-energy astrophysics, it is possible that soon we will have another way of looking at them in the lab using laboratory experiments, in particular laser plasma with the the newly emerging class of lasers called multi-petawatt lasers that may be able to create such plasmas in the lab. And there are other experimental approaches as well that would be happy to talk about if time permits. But I would like to summarize this slide by noting the following thing, that this traditional plasma physics developed mostly in the 20th century is based on the fundamental physics of 19th century, Maxwell's equations, right, and things like that. Whereas this new extreme plasma physics of 21st century is based on 20th century physics, like relativity, for example, or QED, quantum electrodynamics. So you see, we are kind of 100 years or so behind on both counts, but still we are forward. So we are now using 20th century physics. All right, okay, so all of these remarks lead to a formulation of this field that I would like to call extreme plasma astrophysics, which is basically a systematic inclusion of these exotic physical effects into the existing even kinetic plasma framework. By kinetic, I mean the description of plasma, the most fundamental description of plasma, where particles are described in the full six-dimensional phase space, so with velocity distribution and, of course, spatial information as well. So this extreme plasma astrophysics is, I would say, a very intellectually exciting frontier of fundamental physics, and there is now rapid progress being made in this area due to the confluence of four major factors. These include very significant progress that we've made in classical plasma theory, just analytical theory, and our understanding of these nonlinear collective plasma processes. At the same time, of course, there is very powerful astrophysical motivations coming from, observations of merging neutron stars, coming from the first image of a black hole, for example, by the Event Horizon Telescope. What we see in this image is the light, electromagnetic radiation produced by this extreme plasma under these extreme conditions. And of course, there are many other examples in the last couple of decades, I would say. Then the progress that in our understanding of behavior of such plasmas has been made possible due to the advent and rapid development of very novel radiative and radiative QED kinetic plasma simulation codes, and rapid advancements in computational methods, including multi-scale methods and relativistic algorithms and exascale computing and so forth. So this computational component has been a major driver in our progress. And then finally, as I mentioned on the previous slide, we now have perhaps somewhat lagging behind the theory and simulation, but nevertheless very intriguing and exciting experimental component using high-intensity lasers. Okay, right. Okay, now let me slow down perhaps a little bit and say a few things about these plasma processes themselves that we would like to study under these extreme conditions. And I would start by, again, from astrophysics. I would say that we observe that many astrophysical plasmas, astrophysical objects, shine meaning that they produce light that we observe. And the light, again, spans from radio through optical, X-rays, and gamma rays. And many of these sources are actually extended sources. So not point-like source, but let's say this famous jet in the M87 galaxy spanning, tens of kiloparsecs across, or the Crab Nebula, which is a parsec across, and so forth. So these are extended sources. They shine brightly across the electromagnetic spectrum, including in gamma rays and high energy radiation. And if one tries to analyze how this light is produced, one immediately finds that the radiative cooling time of the particles producing this emission is often very short, much shorter then the travel time of this plasma from the central source, let's say from this black hole or from the pulsar, from the Crab pulsar in the center of this image. And what it means is that there must be some in situ local processes that accelerate, that dissipate energy somehow and accelerate particles, including causing non-thermal particle acceleration with extended power laws of particle energy spectra. Well, so this dissipation and particle acceleration is indeed the result of rather complex collective plasma processes. And when we think about these processes, we start with sort of assessing the energetics. What is the source of free energy available to power this radiation? And the two typical ones, the main ones in astrophysics, are bulk kinetic energy of the flow or magnetic energy, or in other words, Poynting flux. Both of them are quite ubiquitous. However, in order to dissipate this energy, so to tap it and convert it into heat, non-thermal particle acceleration, and ultimately radiation, one needs to have some sort of instability, usually that results in some very active dynamics, and quite often, almost ubiquitously, just very general arguments, right, lead us to believe that these processes are triggered by instabilities at quasi-two-dimensional singular sheets or singular surfaces, interfaces. So a situation where you have two regions separated by some quasi-two-dimensional surface across which the plasma parameters change rapidly. An example of this is a shock, for example, when you have this surface perpendicular to the plasma flow, and most of the energy initially resides with the bulk kinetic energy, that produces a shock which dissipates energy, which is shown in the simulation here. Alternatively, you may have a situation where the source of energy is also bulk kinetic, but the surface across which the plasma flow changes is not perpendicular to the flow, but parallel to the flow, so tangential. In this case, you have conditions suitable for the excitement of the Kelvin-Helmholtz instability shown here. But again, releasing some, tapping into the kinetic energy of the flow and dissipating it. And of course, in the case of magnetic field, the suitable quasi-two-dimensional singular structure is an electric current sheet across which the magnetic field changes rapidly. And that's the setting for a fundamental plasma process called magnetic reconnection. I will talk about this a bit later. Should also say, however, that in all of these cases and in many other cases, even though the underlying structure is different, the underlying instability is different, if you look at the long-term nonlinear development of all of these instabilities, especially in a large system with a large separation of scales and in 3 dimensions, what you invariably find is that they all lead to turbulence at the end of the day somehow. So therefore, understanding plasma turbulence is actually, in a way, one could say, is key to understanding the long-term behavior of any kinds of plasma physical processes releasing energy. In this talk, however, I will focus mostly on magnetic reconnection. All right. Now, but before I want to get there, I would like to emphasize this point that even though I just told you that these processes are complicated, they are complicated in their operation, but they're not necessarily complicated in the way they set up or can be described. So let's look at this cartoon, for example. So this is the typical configuration that we study in the field of plasma physics and plasma astrophysics. Extreme or not extreme, just traditional as well. You have, let's say, you have a 2-dimensional box, and you have, magnetic field going to the left, magnetic field going to the right. They're separated by this thin current sheet. So kind of very simple. You have 2 regions which are uniform. Each one of them is uniform. There is some straight magnetic field. Maybe there is some thermal plasma. Nothing is moving initially, and then you have just a boundary between them. But interestingly, however, this cartoon, so that's what magnetic reconnection is, right? So then you ask, what happens to this? And what happens to the system is a very complicated process that we will talk about later. But you see, the setting itself is extremely simple and can be described in terms of very few parameters. And an interesting thing is that this general sketch is sort of ubiquitous. It's important for a broad variety of processes. So here, these blue arrows are magnetic field lines, and that's the letter B. That's magnetic reconnection, but one could also have exactly the same sketch, except that these lines are the velocity streamlines, and then that describes the velocity share, and that's the setting then for Kelvin-Helmholtz instability. So you see very simple pictures describing very different instabilities, but still it's a very simple sort of setup. Another example is this. If you just take some plasma, right, let's say electrons and ions, maybe even in thermal equilibrium, and then you just start shaking the box by applying some force to the plasma in a time-dependent manner, then what you find is you drive turbulence, right? Again, a very simple setup, very simple driving, but results in a complicated process of turbulence. So, processes like this, I would say, they constitute a significant fraction of what we do in plasma astrophysics. And I would call them collective plasma processes, all kinds of waves and stabilities, and as we saw, reconnection, but also shocks and so turbulence and so forth. However, this is not everything that we do. Researchers in plasma astrophysics are brave people, and they also, all right, so that's this. They also attacked global problems, and this is the approach that is more natural to astrophysicists as opposed to physicists. So here there is a distinction here. Plasma physics researchers like to deal with simple setups and studying processes. Astrophysicists are interested in systems as a whole, in astrophysical objects like neutron-star or black hole. So they would simulate on a computer the entire global system, which is a complex machine with different parts. And yes, and nevertheless, they're doing it quite successfully. And then finally, there are things in between. So sometimes people would, to trying to bridge the huge gap between these two approaches, would do something in between. But in all of these cases, the setups are different, the scales are different, but the kind of questions that we ask are quite often very similar again. And there is a short list of classic questions, such as how energy is dissipated, how the dissipated energy is partitioned between electrons and ions. So that's a very important question, in particular in astrophysics of accreting black holes. Then how does non-thermal particle acceleration work, right? So in addition to just heating the plasma, you produce this extended Pauli tails of extremely energetic relativistic particles. So how is that happening? Then, as I said, quite often one finds these motions resulting in turbulence, and one wants to understand the statistical properties, like the spectrum of this turbulence, and also of coherent structures of magnetic fields and flows. So all of these questions are quite common to space physics, to solar physics, and to high-energy astrophysics. However, in this extreme high-energy astrophysics, we also add a couple new questions, such as how light is produced, right? How do these processes power the electromagnetic radiation, let's say, right? What's the spectra and so forth. And also, if there are QED processes involved, then one may ask, what is the efficiency of this process in producing electron-positron pairs? Okay. So that was the scope of the extreme plasma astrophysics and extreme plasma astrophysics. And now let me say a few words about the methods, the tools that we use. And of course, as in any field, we always start with analytical theory. So that's always the foundation, I would say. And there is a lot of research going on in just purely theoretical research. But at the same time, there is also the main component, I would say, is simulations, which have made a lot of progress in the last couple of decades, including, and they do incorporate all this additional rich physics. So there are, for example, radiative, general relativistic, magnetohydrodynamic codes, which are used now routinely to study accreting black holes, right? So they include special relativity, general relativity, radiative effects, and of course, all the complications of magnetohydrodynamics. But this is at the level of the fluid description. But what I would like to focus on is even more fundamental level of kinetic plasma description, where the plasma is described not as a fluid in three-dimensional space, but as a fluid in six-dimensional phase space. And we now have very powerful numerical tools to study this, in particular, particle and cell codes. Well, particle and cell codes have been developed a long time ago and have been used in plasma physics successfully. But what happened relatively recently is the inclusion in the particle and cell algorithms radiative effects. So I should say that most of existing particle and cell codes are already relativistic from the start, special relativistic. But now in both laser plasma, first in laser plasma community and then in astrophysics, researchers have developed a lot of, several very sophisticated codes that include self-consistently the radiation reaction on the emitting particles at the individual particle level, and consequently calculate the self-consistent radiative signatures of this process, such as radiation spectra and light curves. Some of them also have quantum electrodynamics modules, allowing one to study pair production, for example. And there are also a small set of codes, in particular this GRPIC code, which includes general relativity. So that makes it suitable for studying magnetospheres of black holes. And these codes, of course, are quite advanced also computationally. The simulations that people run of these processes are quite demanding, using often hundreds of billions of particles and computational grids on the scale of 1,000 cube, or now even more. And then, so these are just some examples. I don't know, this is a simulation of turbulence. This is a two-dimensional projection, but it's a three-dimensional simulation. And this simulation here is an example, if I can get it running. Let's see. Yes. Oh, here we go. This is just a two-dimensional simulation of magnetic reconnection in the presence of radiation. Well, and then again, as promised, there is also high energy density laboratory plasma physics, which is a field of its own. It relies mostly on lasers, and there have been rapid progress in laser intensity in recent years. So there are now upcoming lasers in the multi-petawatt range that we hope will allow us to access this relativistic realm and to create even relativistic pair plasma in the lab, and then use that as a platform to study these extreme plasma processes. But I should also mention that lasers are not the only game in town. There are also other approaches, such as pulsed power, like Z-pinches, basically, at a number of labs. Okay. All right. Now, one of the main aspects, so there's what are the novel aspects of extreme plasma astrophysics as opposed to just plasma astrophysics? I said one of the main ones is radiation, right? Is the interaction of plasma with photons, with electromagnetic radiation. And at the level of an individual particle, this takes place by including the radiation reaction force into the equation of motion. So here, this is the relativistic equation of motion for a particle with a usual Lorentz force, electric and magnetic force shown here. which is routinely included. And in these extreme conditions, one needs to include also the radiation reaction force. Now, for relativistic particles, with which we are mostly concerned, the radiation reaction force actually is quite simple. It takes the shape of a friction force, so acting in the direction opposite with this minus sign to the particle direction of motion. This is because when the particle is relativistic and it produces light, the photons that it produces are beamed along the motion of the particle itself, right? And therefore, when the emitted photons take away their energy and momentum from the particle, this effectively creates a back force on the particle itself. So the result is this this radiation reaction force that is opposite to the particle equation, the particle direction of motion, and it's proportional basically to the emitted power by the particle. In terms of the actual radiative processes, the two main ones in astrophysics, in high energy astrophysics, are synchrotron radiation, when a charged particle, a relativistic charged particle, like an electron, moves in a magnetic field, it radiates with a power which is proportional to the energy density of the magnetic field, b squared over 8 pi, and the energy gamma, or the Lorentz factor of the particle squared. And another process, also quite important in astrophysics, is inverse Compton scattering. Let's say, basically, when you have a particle moving not through magnetic field, but through an ambient field of soft photons with some radiation energy density, which I also denoted as U, right? Then it collides with the soft photons all the time and scatters them, upscatters them in the direction, again, in the direction of motion of the particle itself. And that results in an effective Compton drag on the particle with the emitted power that has very similar structure. You can see in both of these cases, the radiated power has very similar mathematical structure. There is Thomson cross-section in both of them, speed of light, and then the radiation energy density here and magnetic energy density here, and in both cases proportional to the square of the energy of the particle. What it means is that the most energetic particles suffer more strongly from radiative losses, right? Because the radiative losses goes as energy squared. And that's why inclusion of this self-consistent radiation reaction force is particularly important in high energy sources, like black holes and neutron stars. So this is what happens from the point of view of an individual particle, but from the point of view of a plasma as a whole, as a fluid, the manifestations of this radiation reaction force are as follows. One can first list here the radiative cooling. So basically, plasma radiates, that takes energy away, so plasma cools down. Then there is also radiative drag on bulk motions. When the plasma moves rapidly, it can lose its energy, lose its momentum to radiation, and that therefore radiation acts as basically a friction force. It also, this radiation reaction force also affects electrodynamics of this plasma by providing a source of resistivity. So, rapidly moving electrons and positrons carrying currents suffer from this drag force, and that acts as effective resistivity. And then finally, if the energy density and the particle number density are high, then the emitted photons can be reabsorbed or scattered somewhere else in the plasma. And that results in a radiation pressure. And all of these fluid level manifestations are indeed important in environments of black holes and neutron stars. Now, there is one more aspect of it that I would like to mention here, and that is that, radiation is important in high energy astrophysics, not only because it affects the plasma itself and affects the collective plasma processes, but also because it is radiation that quite often, almost always, provides us with the only observational probe into this astrophysical system. So unlike in the Earth magnetosphere or the solar wind, where we can launch spacecraft and measure the plasma processes locally with high precision and all kinds of quantities. In astrophysics, we don't have that luxury. The only information we obtain is from observations, from using telescopes. And what we're observing is, apart from this multi-messenger component, most of astrophysics is observations of electromagnetic light. And so in order to figure out anything about how these astrophysical sources actually work, we need to understand what kind of radiation signatures, observable radiation signatures, are produced by a given plasma physical process. So if energy is released, let's say in magnetic reconnection here, right, it powers some non-thermal particle acceleration. So one can ask, what are the spectra and light curves? A light curve is a luminosity or brightness as a function of time, right? So what are the things that we can observe and how they are relating to the underlying plasma dynamics? In other words, how, let's say, a reconnection layer literally looks like in the most literal sense. Okay, so that's what we do in plasma astrophysics. Okay, so that's the same, I guess. Right. And now in the last maybe 10 minutes or so, let me focus on one particular example, and the one that is most dear to my heart. I have been working on this for a long time. And that's the process of magnetic reconnection. Okay, but before talking about magnetic reconnection, let me sort of, to set the stage, let me first talk about magnetohydrodynamics, because I understand this, the audience here is not necessarily plasma physics or astrophysics audience, but perhaps many of you are theoretical physicists who are outside of the field. And so I would like to say about a few words about magnetohydrodynamics, and in particular, ideal magnetohydrodynamics. So astrophysical plasmas are excellent electrical conductors. What it means is that in the rest frame of a co-moving with the plasma, the electric, like in an ideal conductor, the electric field has to vanish, like this. But the electric field in the laboratory frame, sorry, the electric field in the co-moving frame, E prime, right, is equal to the electric field in the laboratory frame plus this correction. And so where U is the bulk velocity of the plasma and B is the magnetic field, and of course C is the speed of light. So that equation then is called the ideal MHD Ohm's law. It provides a relationship between the electric field and magnetic field in moving plasma. If we couple this with Faraday's law, which is shown here, one of the Maxwell's equation, we obtain the equation that is very important in plasma physics in general, and it is known as the ideal MHD magnetic induction equation. This equation basically tells us how magnetic field, which is function of space and time, how it is evolved in a moving magnetized plasma. You can see this is basically a transport equation. This is equation for advection of magnetic field with the flow velocity u. But because magnetic field is a vector quantity, this transport equation has a bit more complicated mathematical structure with these cross products. But basically, you see it's a derivative of a product of velocity times that field itself. So it's almost kind of intuitive, except apart from these cross products. And that's how vector divergences, vector field, like magnetic field, gets transported by the flow. This equation has very powerful consequences. In particular, the so-called ideal MHD flux freezing theorem, or Alphen's flux freezing theorem, was derived by Alphen in the 1940s. And the way to describe the consequences are quite simple and quite intuitive. What one finds by applying this equation is that magnetic field lines in a moving plasma are not just some abstract field lines, but they attain a material property. They become like spaghetti in a soup, if you will. That's the common analogy. They move together with the plasma. So the plasma motions can become quite complicated, and they drag the field lines with them. They can stretch magnetic fields, they can twist magnetic fields, tie knots of magnetic field lines. So a given magnetic field line is preserved as a fluid line, basically. Each point on the magnetic field lines moves with the velocity of the plasma flow. One important thing, however, is that these field lines, therefore, they can be distorted quite dramatically, but they cannot break. They cannot change the topology of the magnetic field. And that's a very fundamental result in plasma physics with a lot of consequences. Now, this flux freezing theorem applies almost everywhere and almost all the time in large-scale plasmas in the Earth magnetosphere, in the solar corona, solar interior, astrophysical objects, and so forth. However, it is it is quite common. It happens almost everywhere, but not quite everywhere. And specifically, sometimes it gets broken. And it gets broken by this process that we call magnetic reconnection. It's a non-ideal plasma process where magnetic field lines literally change their connectivity, reconnect with each other, changing magnetic topology. And in the process, they can release magnetic energy and energize the plasma, right? So magnetic reconnection can be described in this sort of simple cartoon where you have these blue field lines coming from above, like one region, and red field lines coming from below. They come together, and then at this point in the center, they literally change the connectivity. They reconnect. This process is not allowed in ideal MHD, but happens in real non-ideal plasmas. And then they move away in the horizontal direction here, right? But having changed the connectivity. And when they're moving out, the magnetic tension of these newly reconnected field lines accelerates plasma flows to very rapid speeds. An essential requirement for this process to occur is the existence of a very thin current sheet, which is depicted here, across which the magnetic field changes rapidly, because it is the simple reason for this is that ideal MHD applies almost everywhere, but it gets violated where there is a very strong electric current density, and that happens in this sort of quasi-singular current sheet. And it only needs to happen actually at one point, at the so-called X point, for the topology to change. At this X point, or in some vicinity of it, there is also a very powerful, very strong electric field out of the plane, and the electric current is also out of the plane here. And this is simply because if you want to transfer magnetic flux from one region to another, by Faraday's law, you have to have electric field everywhere, including here at the center. And this electric field cannot be described by ideal MHD. So this process of magnetic reconnection allows plasma motions and plasma processes that would have been forbidden in ideal MHD. And this violation happens suddenly. So this reconnection, the system may be sitting there accumulating energy for a long time, and then quite suddenly reconnection gets triggered, and now plasma can move in different ways. And in the process, it can release energy that has been stored in the magnetic form and give this energy to the plasma flow, to heating the plasma, non-thermal particle acceleration. So that's a very powerful energy conversion process. All right, so let me skip this sort of more modern view of this process when we have not just a single X point, but in a large system you have essentially a fractal structure, a self-similar structure with multiple X points, multiple reconnection sites. In this case, in two current sheets, and there are all kinds of complicated dynamics going on. But I want to say that this process of reconnection has been studied for a long time, and in particular in the context of space and solar physics. It is this process that we believe is responsible for solar flares and also for geomagnetic storms and processes like generating aurora borealis in the Earth magnetosphere and leading to non-thermal particle acceleration. Because it also has been observed in the lab. In particular, it is associated with so-called sawtooth crashes or sawtooth disruptions in tokamaks, magnetic fusion devices. And because it has been so important, people have also conducted dedicated laboratory experiments to study it, such as this magnetic reconnection experiment at Princeton Plasma Physics Lab, shown here, but also experiments using lasers and pulsed power machines. More recently, I would say in the last 20 years or so, the importance of reconnection has been increasingly recognized in astrophysics as well, in high energy astrophysics in particular. And we now believe that reconnection plays an important role in all kinds of especially violent flaring phenomena, all kinds of bursts and flares in systems like the pulsar wind nebula, like this Crab nebula here, accreting black holes in jets, so powering all this emission along the M87 jet, perhaps in the magnetosphere of the inner part of the accretion flow onto the same M87 black hole, and gamma ray bursts and many other systems. So there is a wide recognition that reconnection may be happening in these systems, but I would say that in all of these systems, reconnection happens in the radiative regime. So unlike the Earth magnetosphere, in order to understand reconnection in these environments, one really needs to understand how it interacts with radiation, in particular radiative cooling. And indeed, there has been a lot of progress in the last decade or so, I would say, using particle and cell simulations to study the effects of radiative cooling on the process of reconnection. So I'll just show you, we're running out of time, so maybe I'll just show you just a movie just to illustrate things. So this is how reconnection happens in 2D. So this is not fully realistic. This is a two-dimensional simulation, but it's particularly kind of dramatic. You can see these blobs of plasma, energized plasma with high pressure, surrounded by magnetic field lines. The magnetic field is not shown here, but you can see and appreciate the complexity of this resulting dynamics with these plasmoids. They have high density and temperature, and they're shining brightly. So if you were to look at the system, this is what you would see. This would be like fireballs or light bulbs moving around with, in this case, it's a relativistic reconnection. So with relativistic speeds, starting with a simple current shed, it goes unstable to reconnection and results in all this complicated dynamics. And let me just briefly describe the effects of radiation reaction or radiative cooling on a particularly important aspect of this process, which is the non-thermal particle acceleration, the spectrum of particles. So here I'm showing the results of, again, particle and cell simulation of a relativistic reconnection with radiative cooling in 3 cases. In the case on the left, there is no cooling at all. And what you find is that reconnection is a very powerful particle accelerator producing a spectrum of particles. You can see here the different lines correspond to different times, but basically what you see is a very extended over 2 orders of magnitude power law distribution function or spectrum of energized particles to very high energies. But then if there is radiation reaction that limits this particle acceleration, and as I mentioned earlier, it specifically affects highest energy particles. So if the strength of radiation reaction, which is sort of denoted by this, I will not go into the details here, but it's some intermediate radiation reaction strength. What you'll find is a broken power law. So you have at lower energies, you have this uncooled power law, and then at high energies, that sort of it steepens. It becomes hard, so it becomes steeper here. And then if the radiation reaction strength is increased even further, then you will lose this powerful non-thermal spectrum altogether, and it all becomes very steep here. So we now have computational and theoretical tools to study these processes in detail at the kinetic level and produce all kinds of radiation signatures. One of the most dramatic manifestations of this is the is not just the energy spectrum of the particle, but the angular distribution. And it turns out that the energized particles in this non-thermal tail, they're not quite isotropic. And the light that they produce, the photons they produce, is also not isotropic. But especially at highest energies, it tends to, the particles and the radiation tends to focus in some narrow beams with small solid angles. And these beams are flying around, so pointing in different directions. So in these angular maps, you can see the sort of essentially quasi-isotropic distribution of electrons in direction at low energies, but at higher energies, it becomes highly structured. You can see there are specific fans, specific directions in which the photons are shining. And all of this has very dramatic observational consequences. Okay, so I think we are running out of time. Is that right?
Yes, yeah, it would be good if you could wrap up.
Right. Okay, great. Yes, so thank you.
Yeah.
Right, yeah, so yeah, I just had a few slides. I can skip them in principle. I can just try to briefly go through them. Of one of the most important examples of this in astrophysics, which is reconnection, relativistic reconnection with synchrotron radiative cooling in the magnetosphere of a pulsar, in particular, the most famous pulsar, and the object that is the most observed object on the sky outside of the solar system. And that is the Crab Nebula shown here. Inside of this Crab Nebula, which is about a parsec across, so quite large, but deep inside of it, there is a neutron star, the Crab pulsar, which is one of the first and sort of most iconic pulsars. It's basically, it's a rapidly spinning 30 times a second, strongly magnetized with 10 to the 12 Gauss magnetic field neutron star, just 10 kilometers across, and it produces these pulses of electromagnetic light from radio with a very extremely broad spectrum. So this is the spectrum of this pulsed emission. You can see it starts here. It's not even the full spectrum, but it covers from radio to optical, many orders of magnitude, and going into giga electron volts, and even now actually even beyond hundreds of giga electron volts gamma rays. And in particular, you can see that there are two peaks in the spectrum. There is a lower energy peak, basically in the X-rays, and then there is higher energy peak in gamma rays and GeV gamma rays. And one would like to understand how this is produced. And I'll just briefly say that if you take a magnet, it has a dipole magnetic field, right? If you start spinning it around, what will happen is that is what's shown here. These are the meridional magnetic field lines. Everything is axisymmetric. This is an axisymmetric simulation. There are field lines that extend beyond the so-called light cylinder, which is this radius here. The light cylinder is the distance at which the point rotating with the angular velocity of the pulsar, so with the angular velocity of these field lines, would be moving with the speed of light. And for the case of the Crab, which is rapidly spinning, that is about 100 times larger than the size of the neutron star itself. So the neutron star is 10 kilometers, the light cylinder is 1,000 kilometers away. So beyond this point, the magnetic field lines cannot stay in co-rotation, cannot have a dipolar geometry, but they have to open up. And this is what happens here in these lines. You can see that the field is splitting up, opening. The color here shows the toroidal component of the magnetic field. And you can see that it in the inner, in the inner part, there is no magnetic field. It's basically just a rotating dipole here inside of the light cylinder. But outside, there is a reversing toroidal field. So in this way, you can see that there is a natural current shed that is produced beyond the light cylinder, extending to large distances, the equatorial current shed. And across this current shed, magnetic field reverses, and that is a natural place where reconnection happens. And this is, in fact, is we believe, one of the key places which is critical to understanding the operation of any pulsar magnetosphere, including the crab. This equatorial current should be beyond the light cylinder. It's a source of reconnection, but as I told you earlier, neutron stars are extremely powerful magnets. In the case of the crab, the magnetic field at the surface of the neutron star is on the order of 10 to the 12 Gauss. At the light cylinder, it's much weaker, of course, but it is still a mega Gauss, so 10 to the 6 Gauss. And if you're trying to reconnect, or 100 Tesla, if you're trying to reconnect this field, the energy release is so powerful that it hits the plasma to extremely high temperatures. The particles become relativistic, and in this very strong magnetic field, they're producing very intense synchrotron radiation. The synchrotron radiation cools the plasma, and then what happens is that the plasma cools down due to this synchrotron cooling. However, it has to maintain the pressure balance with the magnetic field. So you can see sort of here in this cartoon, there is a magnetic field on both sides of this current sheet, where the magnetic field and magnetic pressure is strong. There has to be a pressure balance across the current sheet, where the plasma pressure inside balances this magnetic pressure outside. So in this sense, the plasma pressure here has to be very high, but the plasma cools down. As a result, the plasma has to compress to maintain pressure balance. And if one just makes very basic estimates of combining this pressure balance and the synchrotron cooling and Maxwell's equations, essentially, one can estimate the key plasma parameters inside of this current sheet, and one can find that indeed most of the energy that is released through this process is radiated away with synchrotron radiation. The characteristic temperature of the plasma here is in the range of giga-electron volts. So these are very relativistic electrons. The density has to be rather high as well, but not extremely high. So the plasma compresses, and if there is not enough plasma there, then it will be created, because the synchrotron radiation that is produced by this layer is in the giga-electron volt range. It's easily capable of producing pairs. So the reconnection process here not only releases magnetic energy, but it creates its own plasma, right? Through pair production powered by this annihilation of synchrotron photons. And at the end of the day, one goes through this exercise, one finds that the characteristic plasma kinetic scale, such as the Larmor radius of the particles, and therefore essentially the thickness of this current sheet, turns out to be very much on human scales, like tens of centimeters or meter across. So of course, the longitudinal scale is comparable to the light cylinder, which is 1,000 kilometers, but this distance, but the thickness is like a meter or less. Now, this has a lot of observational implications that one can investigate. The most important one is perhaps indeed this is what powers this peak, this GeV pulsed emission from the Crab pulsar. Also, the inverse Compton scattering by the same 100 GeV electrons can produce gamma ray emission at even higher energies, which is now observed, very high energies. And then finally, interestingly, as I told you, a reconnection process in reality is never simple, but it has these instabilities, all kinds of plasma structures, a hierarchy of plasma structures at different scales. They're moving around, these plasmoids. They sometimes merge with each other. They grow in size, they collide and do all kinds of things. As a result, these collective plasma motions at scales comparable to the thickness of this plasmoid of the current layer, and then larger also, produces coherent emission. So not just individual high energy emission produced by individual particles, but coherent large scale motions of the plasma may power radio emission, which is in fact what we observe. from the sources, right? And just to end here, finally, this was just simple estimates. However, now there is a whole industry. In the last 10 years or so, there are research groups at Columbia University, at Princeton, and Maryland, and many other places that study this complex extreme plasma astrophysics at the kinetic level with the inclusion of radiation and pair production, with particle and cell simulations at great sophistication, and resulting in very increasing the predictive power of the theory, capable of producing observational signatures that can indeed be compared with observations in great detail. So because of these numerical simulations, we've made tremendous progress recently in understanding, well, not just reconnection, but just in general, how these extreme astrophysical systems operate. Okay, so let's okay, and then so just it's not only radiation, but also pair production that is being now included routinely in these simulations due to various QED processes. Okay, so I guess thank you very much for your attention. I will stop here, and thank you again for the opportunity for me to give this talk. This is the summary. I would like for you to take away this idea that we now have a burgeoning and vibrant new subfield of theoretical physics that we call extreme plasma astrophysics, and that can be described as a kinetic plasma physics with some non-traditional exotic physical elements such as special and general relativity, pair plasma composition, radiation, pair production, and quantum electrodynamic effects in general. There is a rapid progress being made here due to theory and computation, in particular these sophisticated numerical codes that study these plasma processes from first principles very rigorously while incorporating these effects. And then finally, we are on the verge of being able to study these processes, hopefully in the next decade, in the lab using new facilities that are coming available. Okay, thank you. Right.
Okay, thank you, Dmitri, for this very nice overview of astroplasma physics and some recent frontiers as well. So the floor is now open for questions. Are there any questions from the audience? If you do, then
for a bit too more time. Okay.
And or
too much time.
Yeah. It's okay. Professor Her?
Hi, can you hear me?
Hello. Yes.
Hello.
Hello.
Thank you very much for very nice review of extreme plasma astrophysics. It's quite impressive. Actually, I'm teaching plasma physics at UNIST, which is 1 hour driving from Yongdae's place. And I myself studied a little bit about radiation reaction, especially the classical way of modeling. And during the study, I learned that there exist several different kinds of ways to model the radiation reaction. And depending on what kind of model you choose, probably you can obtain different results. So in that sense, in your magnetic reconnection research, depending on what kind of radiation reaction model you choose, probably you can obtain different results. And I wonder if we were studying your problem in that way, and I also wonder, studying the astrophysical magnetic reconnection data can be a way of establishing which one is the correct model of radiation reaction.
No, that's a tall order. That's a challenging. But thank you. Yes, thank you for pointing this out. I think actually our understanding of the radiation reaction force, even the classical classical regime has been mostly based on the research done not in astrophysics, well, at the most sophisticated, at the most sort of complicated level, or not complicated, I should say, rigorous, at the most rigorous level, but by research done by people who study, laser plasma, or just laser processes and laser plasma interactions. Indeed, so people there in this field have been thinking more carefully, I would say, and about different aspects of this. And in astrophysics, we usually just take whatever is available, well, whatever our colleagues tell us to do. So the most common approach incorporated essentially in all of these codes is the Landau-Lifshitz. It's called the Landau prescription. Maybe indeed kind of justifiable for many of these systems, because one deals with usually the particles are ultra-relativistic, the ones that we care about are ultra-relativistic. The fields, the magnetic, let's say, fields that interact with exist on scales that are large. So like in lasers, you have a wavelength, which is sort of, which is sinusoidal, right? Sinusoidal variation over a micron in size, right? In astrophysical plasmas, usually the fields are more extended compared to radius even. Although not always, and in principle, one needs to worry about this. But I should also say that this is a relatively new field in astrophysics, physical application. So, for example, I would say, whereas the inclusion of radiation reaction in particle and cell codes has been done in, I think, in laser plasma field long time ago, and has been used there in many simulation studies. In astrophysics, with astrophysical applications, it really only started around 2012, 2013.
Okay.
With one exception. There was one exception. There was the very first, really, I would say, pioneering work, the first simulation of an astrophysical plasma process, which happens to be reconnection, actually. So a relativistic reconnection with a synchrotron radiation reaction was, so the first work was by Jarocek and Hoshino in 2009, so 15 years ago, right? And then in 2013, my postdoc, I had Benoit Cerruti, who was a postdoc with me at the time in Colorado, developed a radiative particle and cell code, which I think was the first to develop in astrophysics, but well behind far behind the developments in laser plasma. And since that time, there have been several other codes developed, and we are now also using. So in astrophysics, we are now also trying to connect with the laser plasma community and to tap into the expertise there. So we are now using codes developed there for our research as well, like the OSI code in particular. Right. Now, I appreciate your suggestion to use astrophysical observations as a way to tell which form of the radiation reaction force is right. But I would be skeptical about this, I have to say. The reason for this, the reason for saying this is that our understanding of the astrophysical systems is very indirect. I mean, it's primitive and very indirect. So, and in contrast to laboratory, even laboratory experiments. So in a laboratory experiment, you know what is the system you're dealing with in advance. You're creating, designing it, right? And then you can do the experiment, measure things. You can simulate it, measure things in the simulation, and compare. But in astrophysics, unfortunately, you don't actually know what you're dealing with to start with.
All right.
Right. So you don't know, for example, what the magnetic field strength is. So let's say you observe gamma ray flare from some remote object, or maybe pulsed emission from a pulsed magnetosphere. You are then trying to rely on theory and simulation in order to deduce. So you're trying, you're relying on your theoretical understanding being solid in order to deduce what the underlying physical parameters are. But there is no way for you to kind of to know them independently. So yeah,
actually, I'm a little bit familiar with that kind of approach because in my department we also have some two astrophysicists. Okay, Doctor. Okay, thank you very much for your discussion.
Thank you. Great question. Yes, thank you.
Okay, are there, I guess, around 10 people left because of the time, obviously, understandably, but are there any questions, other questions from the audience?
Yeah, actually, I want to ask one question.
Sure. Go ahead.
Please open slide number 17.
Okay, so I need to share my screen again, right? Just give me a second here. Slide number 17. Okay, let me scroll. How do I? Okay. Actually, let's do like this. Okay. This is this the slide?
Yeah, actually, I was wondering what these additional terms from this radiation reaction force. So my question is about these additional force terms because of this radiation reaction.
Yeah.
So my question is, can I derive this additional force from the moment of the Vlasov equation?
No, you don't derive it from the Vlasov equation. You substitute this into the Vlasov equation.
So this is kind of a new modification on the kinetic model, so that it's
no. Well, this is not even new. This is not even new. This equation here, I mean, talking about this equation, this is just the equation of motion for a single particle. Right, Vlasov equation is the kinetic equation for the entire population of plasma, but this is for a single particle. And if you drop this, this term in the red oval, if you drop it, and then you use this equation to obtain the Vlasov equation, the classical Vlasov equation, but relativistic. I mean, this is a relativistic version of it, but other than that, it's just it will give you the usual Vlasov equation. Now, in the presence of radiation reaction, there is this extra force that is not normally included in the Vlasov equation, but has to be included, right? And this radiation reaction force, it results in an extra term in the Vlasov equation. And importantly,
So in the present PIC codes, which people have been using, they depend on these Vlasov equations mainly, right?
Well, not necessarily. I mean, so the particle and cell peak codes normally that's what they do. They present a way to simulate the Vlasov equation. However, one can add to them additional things, in which case it will not be quite the Vlasov equation is a collisionless, right, Boltzmann equation.
Right.
But one can add, for example, collision terms. So not radiation reaction, but sometimes people have peak simulations of process that include collisions, just binary Coulomb collisions, right? That is and this is so what we're doing here is sort of along the same lines. We're adding extra physics. In this case, not collisions. So I should say that the processes that I talked about, or there is a large class of astrophysical systems or environments that we are studying here, which in fact have low enough density, and of course they're very hot, that they are collisionless. So the binary collisions quite often are not important, but collisions between, let's say, particles and photons are important. And right, so then one adds this extra term, and what it does, among other things, is that the Vlasov equation no longer preserves phase space volume. Right, so the usual collisionless Vlasov equation, it's a Liouville equation. It preserves phase space volume. This because it's it describes Newtonian mechanics, but this violates that. So you can have you can, for example, lose entropy, right? Which is normal, of course. You have cooling, right? So that's right.
Right.
So this is at the individual particle level. Then what peak codes do, they essentially simulate relativistic, well, maybe one could say relativistic Vlasov equation, but with the inclusion of radiation reaction. But then also if one, for example, takes that equation and take different moments, velocity or momentum moments of this equation, one then can obtain fluid description. And in the fluid description, like the usual, two fluid or magnetohydrodynamic description. And in that description, this radiation reaction force will be present as in this way, as a radiative cooling force. There will be a cooling term, or there will be, all of this, right? Extra resistivity and things like this. Okay.
Okay.
Thank you. Yeah.
Okay. Are there any other questions from the audience? Well, I'll take the liberty as a chair to ask my own question, just a short question. So, many of the situations you described, especially in radiative reconnection, for example, where your temperature is decreasing and decreasing, your density is increasing. At some point, you could have a situation where your coupling parameter, plasma coupling parameter, is of order unity, in which case all your conventional plasma physics goes out the window, and you have to consider like strongly coupled effects. And I asked this question because at Postec, which is the institution I am at, we have actually a strongly coupled plasma experiment where we can actually make these kind of things in the lab. And it turns out they have very, very different material characteristics from conventional plasma. So I guess my question is, have you considered sort of this coupling parameter in various situations, various astrophysical situations, and the repercussions of it?
Yeah, that's a great question, and I have to say that no, I know my colleagues have been concerned with this. Indeed, it's well, astrophysics is a very large and diverse subject, because in the universe you can find really different situations with different physical conditions, including those where non-ideal plasma effects become important, as you said, when essentially when the number of particles in the Debye sphere, becomes small. But at least so far in these in the environments that we are talking about here, that hasn't been an issue or a concern. One can estimate for the plasma parameters we're dealing with, with not just extreme these environments of neutron stars and black holes, but even just like solar wind and the Earth magnetosphere. These plasmas are kind of hot enough and dilute enough that the number of particles is in the Debye sphere is very large. So that is still usually the case. There may be other situations where other things happen. So where one needs to modify the basic plasma framework, indeed, but I guess I would say so far we had other things to worry about, right? So it's just trying to understand the basic operation in the regime that we think is actually relevant. But yeah, I appreciate your question, and it's a very important study. So,
okay.
Yes,
Thank you.
And of course, much more complicated, right, than what we do here.
Yes, yes, yes. Okay, I think we ran out of time by a lot, actually. So I think it would be best to wrap up the colloquium at this point. And I guess we'll virtually give a round of applause for Dmitri. Give a very nice talk.
Thank you very much. Thank you. It's been a pleasure.
Thank you very much, Dmitri.
Sorry for taking up too much time.
No, it's fine. Yeah.
Great. Thank you.
Thank you.
Yeah, hope to see you at another place at another time.
Yeah. Sure.
Okay.
Bye.
Bye-bye.
Bye. Goodbye.